Hello, IB physicists. Let's go ahead and start our first lab of Unit 2. And this is actually going to be our only hands-on lab. I'm pretty sure that I'm correct about that. For this particular unit. It's a really quick unit, and so this is a big fundamental lab we're going to do. And I want you to sort of think about how far you would travel in 10,000 seconds. So you might need to do a little bit of estimating in your head. You might just have a random guess. Take a moment and just sort of think about that random guess. How far would you travel? Let's say you were walking in 10,000 seconds. And so our goal of this unit is to really understand some fundamental patterns in motion. And to start out, we want to think about what variables we're going to look at to accomplish this goal. So take a moment and sort of think about what variables would be useful for you to consider if we're trying to understand patterns in the motion of different things. What would be useful to look at? Well, maybe you recognize that motion involves like looking at something over time. How it moves means it was in one place at one time and another place at another time. So time is going to be one of the things we care about that we're going to look at. And the other thing we're going to be looking at, the other variable we're going to consider is called position. And position is a word that we'll get to doing a little bit more definition of together as a class. But position just means where an object is. So in this lab, we're going to be investigating how does the time I travel affect my position? That's going to be our research question. And so right now I want you to take a moment and pause the video and in your lab notebook record our independent variable, dependent variable, control variables, and make a prediction for what you think a graph of time versus position would look like. You might describe that relationship in words, but have some type of prediction. Oh, and you should also write down your question. So go ahead and pause the video and then come back when you're ready to start moving on and thinking about procedures. So we're going to be doing some specific procedures. I have a little video here that you're going to watch showing you how I would conduct these lab procedures. Unfortunately, I tried to conduct these lab procedures on the windiest day this month so far, so it was a real challenge for me. I recommend if you have a really long hallway or your basement goes the full length of your house, you might find it easier to do this lab indoors. But if it's not too windy outside, it could also be a nice chance to get outside while it's a little bit warmer for the next week or so. All right, so let's talk about the constant velocity lab here. So the key is to walk at the same speed the whole time, and you're going to need some materials that you already have conveniently. You need your measuring tapes from your supply bag. You'll need 2 of them, hopefully not torn. You need some socks. You need 6 socks or other items. I used socks because you could, I didn't feel bad dropping them on the sidewalk. But they were already dirty, and so yeah, I just threw them in the wash. Then you're going to need that audio file that's on Schoology. You'll need to have some sort of long place where you can conduct your lab. I found it helpful to have some Post-its that I stuck down to indicate 2 meters, 4 meters, so I just didn't keep track. And then, of course, your lab notebook and a person that can walk. You could also crawl or jog, but that's doing the most. So the way that this is going to work is I have this audio recording that you can maybe hear a little bit in the background, and it tells you when to drop your sock. And so you're going to drop 6 socks, and so you can see that I'm dropping these socks at specific times, and it's every 2 seconds. So every 2 seconds we drop a sock, and that then gives us a collection of data that we can measure in our lab notebook. Good job, I have my lab notebook and my pen, aren't I pro? And so I'm going to use my measuring tape to measure from the very first sock to the next sock. That's the 2-second position. How far did we go in 2 seconds? Then from the first sock to the 3rd sock, that would be how far in 4 seconds, and so on. I explain this a little bit more in the next chunk of video, so hopefully that will be helpful for you. And if you're still confused, let me know, because this is the data collection is very, very important. So let me know if you're stuck. I stuck some pennies on my measuring tapes to make them like stay on the sidewalk. But I will point out that that didn't work very well. Yeah. So maybe if you have a long hallway or like the basement of your house is long, it might be easier to do this lab inside. Today was very, very windy, so I kind of failed at doing it outside, as you can tell. Okay, so you looked at this video and you saw how I was using socks as my measurement tool. Um, and so I want to talk a little bit about the actual measurement process because that's something that can be a little bit challenging. Um, so, so I'm going to make this visual here a little simpler by taking out the picture of my sidewalk. So here I have these socks that I dropped along the sidewalk, and you should have at least two measuring tapes. You saw that I did the little penny trick on the ends of my measuring tapes to try to hold them down. That actually didn't work super well for me because it was so windy, but it does work really nicely if it's not too windy out, so that you can have a thing that stands still. So the way we're going to do this is I have my starting sock. So I'm going to line up 0 at the beginning of my starting sock. Then here's my meter stick. Oh, it doesn't quite get to the next sock. So this would be time equals 0. This would be time equals 2. This would be time equals 4. I can count sometimes. So I'm going to line up my next ruler. And that means that I'm going to, so here's 1 meter. So I have 1 meter stick here. Nope, that's not the meter stick you're moving. That's the meter stick. So here's 1 meter from the first sock, not quite to the next sock. So it's going to be 1 meter and maybe this is 15 centimeters. I'm making up numbers. You should actually measure. So I'm going to read that off. I'm going to write that in my data table. But then to make my life be just a little bit easier, I would recommend having some other marker you're using, like a Post-it maybe or something else, and just drop something at the 2 meter mark, just so that you don't have to like go, oh crap, what distance was I at? I had prepared some little Post-its that again, I wasn't able to demonstrate doing this on the sidewalk. So that's why I'm walking you through how you would do this here. But I would put something down just so that you have a spot where you can come back to and say, ah, yeah, that's 2 meters. So we've gotten the length to our first sock. So now we're going to get the length from our starting sock to our third sock. So this is going to be 0 seconds, 2 seconds, 4 seconds. So again, I already know this 2 meter mark. I'm going to leave that here. I'm going to take the very first meter tape I laid down, and I'm going to move that forward. And, oh, maybe that does get me to my next sock. Well, I'm sort of thinking halfway through the sock is where I want to measure to. So actually, I'm going to lift up my other meter stick and get these to line up. Come on. So you want to make sure you're trying to do your best to make them line up. So this is 2 meters. Here's a third meter. And here's, let's see, probably it's like 3.09. So 3 meters and 9 centimeters is where my third sock is. So I would write that down in my lab notebook. And then I would go on and actually place this little 4 meter mark right here. Again, just so that if I go, wait, how many meters was it? I don't have to go back to the beginning to get the next sock. So I'll have to move my meter stick to get to my next sock, which obviously you can't see. Because what you are trying to measure is not the distance between each sock, but the distance from the first sock to the 2-second sock, then to the 4-second sock, then to the 6-second sock, then to the 8, and anyway, I could keep going, but I won't because I hope you get the idea. So take a moment and take some notes on this measurement procedure in your notebook. Jot down what's going to be helpful for you to remember, maybe you want to go ahead and just jot down where in this video you're at so that you can go and take your data. Actually, you probably want to write down your data table first. So, but jot down how you're going to do this procedure, and then we'll look at our data table in about, 3 seconds. Okay. So then the thing that you want to consider, even before our data table actually, is thinking about what your measurement uncertainty is going to be for our independent variable and our dependent variable. So our independent variable is time, and it should be some amount of time in seconds. And you should have some reason that that is the amount of time. I will remind you that the audio file that you are using to collect your data is from me looking at a timer telling you when 2 seconds have passed. And so I am a human. That might be a good hint for your measurement uncertainty for time. Then we're going to misspell uncertainty. Then you want to also write down the same. So again, these red things should be written down in your lab notebook. You want to write down the same for your dependent variable position. What will the measurement uncertainty be for your position? So recall that a meter sticks measurement uncertainty is 0.001 meters or 0.1 centimeters. We're going to be recording our data in meters in this lab. But you want to make sure to think about, does that make sense for this lab? I might argue actually that it doesn't, and I think you should reflect a little bit based on this measurement procedure involving the dropping of socks or other similar objects. What is going to make sense for the measurement uncertainty for position? Because this is actually a pretty difficult lab to measure. So you make sure that you have a justification for why you are deciding whatever number you put in here for your measurement uncertainty. Okay, so then you want to go ahead and set up your data collection. Setting up your data table. Notice I have not set this up for you. You need to write in independent variable. What is your independent variable? Well, I actually just told you it was time. So like you'll say IV colon time. You'll write down your plus or minus. That's your measurement uncertainty. Record your dependent variable position. Again, measurement uncertainty. You want little parentheses here that will tell you what units the position is being measured in, what units the time is being measured in, and then you can go ahead and start collecting your data. I would like you to do 3 trials. I know it's a little bit annoying, but this is a really big fundamental lab, and it's going to be helpful to have 3 trials. So we have our data collection. You'll go through that. And then I do want to point out that you want to double check that your column headers have the correct variables, units and measurement uncertainties, so the plus or minus, the units, those would be seconds and probably meters. You want to double check that the precision of your data matches the precision of your measurement uncertainty. So if I go out to the thousandths place value, these numbers should all be recorded to the thousandths place value. If I go out to the hundredths place value, all should go out to just the hundredths place value. If I only go out to the tenths place value in my measurement uncertainty, similarly, I'll stop. Then take some time to calculate your average, your statistical uncertainty, and decide your error bars. Again, remember, error bars are the larger of the measurement uncertainty or the statistical uncertainty. Okay, so then you want to go ahead and graph your data. And so I have created yet another Desmos link for you. So you want to use that in this assignment. It should be linked below to graph your data. And you're going to use the largest error bar for your dependent variable uncertainty. So again, you'll have calculated your error bars. Whichever one is larger here, that's going to be your measurement uncertainty for the dependent variable position. You'll create min and max fit lines. And actually, let's go ahead and look at that. So here is the Desmos template that I created for you. And this is something that I learned how to do only recently with one of you in office hours, which was very helpful. And so just like usual, you'll enter in your data here, time, position. Normally we'll use X for position, but I thought you might not like that. So I went with P. Thought it would be pretty logical. You'll put in your error boxes. And then there's this messy looking stuff here. And this messy looking stuff here is actually super useful for you because what I have done is created draggable lines. So notice there's this purple line and I can drag it around so you can make your maximum and minimum best fit lines just by dragging. I feel so proud about this, guys. Like, for real, I just can't even. It's so cool. Isn't that cool? And look, it gives you the slope and the y-intercept. Isn't that cool? I'm sorry, I'm much too excited about it. Um, but this is going to be really, really useful for you so that you can actually get a really nice max and min line without having to fuss around a ton. Um, there's a bunch of stuff down here you want to not change because if you change it, you might mess up my coding that creates this for you. So this is a little bit nicer so that you can get your max and min fit lines. Let's hop back to our slides here. You'll want to record those in your lab notebook. So you'll have your y variable, which is position, which is in units of meters. Our slope, you should have some units. Our x variable, which is time, and that should have units of seconds, and then you'll have a y-intercept. So make sure that you have your maximum and minimum best fit equations written down. Then you want to go ahead and find your best fit line. This is a little graphic organizer. You could pause here if you'd like to, that we would have used in the classroom, and we haven't been in the classrooms. But it's kind of useful so that you can have a little table to help you calculate your average value of slope, your average value of the y-intercept, the absolute uncertainty for both of them, and then the percent uncertainty for the slope. Then you're going to want to go ahead and make your average curve of best fit equation. Notice that it has the same thing with y variable and y units. Our slope has an uncertainty, both of those have units, and so on. And you want to make sure to record this in your lab notebook. Then you might find it useful to pause the video here because it will stop in like 20 seconds. You want to write a mini lab conclusion in your lab notebook that includes all of these things. Answer to a research question, meaning of the slope. What does the slope mean about your walk? What does the y-intercept mean about your walking? And the calculation for what distance would you have traveled in 10,000 seconds. Then upload to Schoology!